Hey, today's lesson is going to be about the sequence, a fundamental topic in math. We're going to use it a lot. And today we're going to learn what it is exactly and how we should view it, since the sequence, whether we like it or not, is always in the background when we're dealing with high-level math. So first of all, a sequence is a collection of objects. It's enumerated. These objects are going to be usually numbers, and we're going to call them terms or elements, since those numbers are going to be in the shape of variables most of the time. Now, sequences can be either finite or infinite. In our case, most 99% of the time, our sequences are going to be infinite. The general notation is brackets with the elements inside. We're gonna denote those elements as A1, A2, A3, and so on. For example, we can look at this sequence 1, 2, 3, and so on, a simple sequence, or another sequence 1, 1, 1, 1. So just to make it clear, when we have a sequence, A1 is the first element, A1 equals 1, in our case, this example. A2 would be 2, A3 would be 3, and so on. The general term or element in a sequence is going to be denoted by an. In our case, in this example that we have in front of us, we can kind of clearly see that an would be n because it's a simple sequence. It's just 1, 2, 3, and so on. Usually we'll deal with more complicated sequences. Now, once we know how the general element looks like, that would be our sequence rule, and that will describe the sequence for us. If we can find it, great. Let's bring back the other sequence we saw, 1, 1, 1, a constant sequence. Well, in that case, it's also pretty simple. An equals 1. It's a constant sequence. Again, most sequences won't be as simple. Before we move on, let's just present the formal notation of a sequence. We write an in brackets, whether curly or not, and n, the index, runs from 1 to infinity, or from 0 to infinity. Sometimes we start with 0. It can also be a finite series, meaning that it's going to run from 1 to, let's say, 100. But in either way, now we're ready to move on and ask some serious questions. Basically ask, what is interesting about a sequence? What will take our attention about it, and what do we want to find out? Well, in order to do so, first of all, I want us to understand exactly how a sequence looks like. What should we imagine when we think about a sequence? And if we'll do that, we'll know what kind of questions to ask and how to answer them. Okay, so before we start, let's introduce a different sequence than the ones we just saw. A very popular sequence, and we're going to use it a lot in our next lessons. It's going to be the sequence an equals 1 over n. Basically, the general element is 1 over n. Formally, we can write an in brackets and runs from 1 to infinity. And that means that if we write explicitly our first terms, the first term would be 1 over 1, which is 1. The second one would be 1 over 2, which is half. The third one would be a third, a quarter, and so on till infinity. How do we visualize a sequence? Well, for that, we need a coordinate system where the x-axis represents the index of the elements, while the y-axis represents the value of those elements. In our case, A1 would be 1, A2 is going to be half, and just like we said, A3 would be third, A4 would be fourth, and so on and so on. And now we can see our sequence. And when we see a sequence, we know what questions to ask, but even better, we know how to answer them. So before we move on, let's just look at a sequence we already saw before, an equals n. And notice that we can visualize that sequence as well. Now, after we did this introduction, now we can ask ourselves our questions. What would be of interest here? What is interesting about a sequence? Well, the answer is its properties, the properties that it has. The first one we're going to deal with is the property of boundness. We're going to ask ourselves, can we bound the sequence? What does that mean? It means that the values of the sequence can be bounded. To understand it, let's bring back our sequence 1 over n. The values of this sequence can be bounded. We know that the maximum value of the elements in this sequence is 1, the first one. So we can create an upper bound for this sequence if we take a number that is larger than 1. Any number, 1.5, 2, 1.2, is going to be an upper bound for this sequence. All of the elements are going to be smaller than that value. Similarly, we can create a lower bound. In this case, in this sequence, we know all of the elements are positive. They're all above 0. If we stretch a line that is negative, it can be -1, -2, -0.1, and even 0, all of our elements are going to be greater than that value, which means we have a lower bound and an upper bound in this case. Now, this upper bound and lower bounds that I created were arbitrary numbers that were more than 1 or lower than 0. But we can actually create better upper bounds and lower bounds. I can reduce the upper bound and increase the lower bound to create the best bounds I can. But that's a topic for another lesson. Right now, all I care about is can I or can I not bound the sequence? And if we zoom out, we notice that our upper bound and lower bound hold till kinda infinity. Well, we can't go that far, but we understand the idea. We usually denote the upper bound as capital M and the lower bound as lowercase m. And formally, we can say that for all natural n's, an is bounded between m and capital M. Or in our case specifically, an is bounded between 0, the lower bound, and 1, the upper bound. Of course, we could have taken other lower bounds and upper bounds, but the fact that it is bounded is what's important right now. Now, to explore this idea a little bit more, let's look back at an equals n, the first sequence we saw, 1, 2, 3, and so on. And let's ask ourselves, is this sequence bounded or not? So let's draw it, because we know how to visualize a sequence now. And now let's try to bound it. So I think what most of you think is that, wait, a lower bound is simple and easy. We can use the same lower bound, 0, from the previous sequence. We can use also -1 or half. Any of them would be a lower bound for this sequence. What about an upper bound? Is the upper bound from the previous sequence, m equals 1, is that an upper bound? Well, we can tell it's not. Most or all of the elements are greater than this upper bound. So what happens if we increase it to 5 or increase it to 10 or higher? Can we bound this sequence? Well, now that we can see the sequence, we understand that no, bounding it from above is not an option. However high we'll get with the upper bound, there's always going to be elements that are greater than our upper bound. And that just means that we saw a sequence that is unbounded. Okay, we have those as well. Let's go back to properties. The second property that is going to be interesting for us is monotonicity. We're asking ourselves if there is a trend that this sequence is following. Is it going down towards 0 or up towards infinity, or in general it has any kind of direction? As before, let's bring back an equals 1 over n just to understand the idea. So in this sequence, just like we saw before, our elements are 1, half, third, quarter, and so on. Our general element is 1 over n. The next one an plus 1 is going to be 1 over n plus 1 because that's how this sequence works. Now we notice algebraically that 1 over n plus 1 is always smaller than 1 over n. If we notice that, and we know that 1 over n is an, and 1 over n plus 1 is an plus 1, we immediately receive the result that an is always greater or equals, but in this case it's greater, than an plus 1. And if we understand that an represents the general element and an plus 1 the following element, basically what we get is that always the following element is smaller or equals to the previous one. And we can see it. 1, half, third, quarter, fifth, and so on. Now what we did here, we gave mathematical proof that this sequence is decreasing. And that is the idea behind monotonicity, whether our sequence is increasing or decreasing. Now, some sequences don't do either. A very popular sequence, we're going to see it now for the first time, is minus 1 to the n. That means our elements are minus 1, 1, minus 1, and so on. Let's draw it, as always. If we draw it, we notice something very obvious. The first element, minus 1, and the second element, 1, is greater than the first one. But the third element, minus 1, is smaller than the second one. And the fourth element, 1, is greater than minus 1, and so on. Minus 1, 1, and so on. Meaning this sequence is not increasing and is not decreasing. It's just a general sequence. It is not monotone, although it is bounded. Now these two properties that we just learned are very important for us moving forward. And it opens the door for us to talk about what is going to be the most important thing for us in sequences, which is the limit of a sequence. But that's a topic for our next lesson, so see you then.